Welcome. Today we are going to work through one of the most practically important ideas in designed experiments. What happens when you have more factors than your run budget can support, and how a half fraction design lets you move forward anyway, deliberately and with full awareness of what you are trading away. Every experimenter eventually hits the same wall. You have identified 5, 6, maybe 7 factors that might matter, and your budget allows, say, 16 runs. The problem is that a full factorial doubles in size with every factor you add. 2 to the 5 is 32 runs. 2 to the 6 is 64. The budget does not grow with the factor list, so something has to give. The answer that fractional factorial design offers is this: accept a specific structured form of ambiguity in exchange for feasibility, not random ambiguity. Structured ambiguity, where you know exactly which effects are tangled together and you can reason about whether that matters. That is the deal. The rest of this lecture is about understanding exactly what that deal costs and how to manage it. Let us ground everything in a single running example that we will carry all the way through. An engineering team is developing a polymer coating process. They have identified 5 factors they want to study: cure temperature, catalyst load, solvent ratio, mixing speed, and coating thickness. The response they care about is adhesion strength. A full 2 to the 5 factorial would require 32 runs. Their budget allows exactly 16, so they are going to run a 2 to the 5 minus 1, half fraction half the full factorial, 16 runs, 5 factors. Every concept we introduce today will be illustrated with this study. Before we talk about confounding in the abstract, let us look at the actual data structure. Here are the first 8 runs of the coating design. Notice something about the E column, the column for coating thickness. Look at run 1. A is -1, B is -1, C is -1, D is -1, and E is +1. Now multiply those 4 A through D values together. -1 times -1 times -1 times -1 equals +1. That matches E exactly. Check run 2, A is +1, B through D are -1, so the product is -1 times -1 times -1 times +1, that is -1, and E is -1. It matches again. This is not a coincidence. The E column was not set independently by the experimenter. It was derived, computed as the product of the A, B, C, and D columns. That is the defining feature of a half fraction. The 5th factor rides on an existing 4-way interaction. We did not add any runs to accommodate it, but we created a permanent link between E and the ABCD interaction, and we must track that link throughout the entire analysis. To understand why fractionation is not just acceptable, but often sensible, we need to think about what a full factorial actually estimates. In a 2 to the k design, the total number of estimable effects is 2 to the k minus 1. For 5 factors, that is 31 effects. But how many of those do we actually care about? Main effects: 5. Two-way interactions: 10. That is 15 effects that a practitioner would genuinely want to know about. The remaining 16 are 3-way, 4-way, and the 5-way interaction. The sparsity of effects principle says that in most real processes, only a small fraction of all possible effects are truly active, and the active ones are almost always main effects and low-order interactions. High-order interactions are rarely physically meaningful, and even when they exist, they are usually too small to matter practically. So a full factorial spends enormous resources estimating effects we would discard anyway. Fractionation formalizes that decision up front. Let us make the sparsity argument quantitative. If we define low-order effects as main effects plus two-way interactions, then the fraction of all effects that are low-order is k plus k times k minus 1 divided by 2, all divided by 2 to the k minus 1. As k grows, that fraction shrinks rapidly because the high-order terms multiply exponentially while the low-order terms grow only polynomially. Here's the table. For 3 factors, 85.7% of all effects are main effects or 2 ways. Almost everything is low order. By 4 factors, it drops to 66.7%. At 5 factors, our coding study, the highlighted row, only 48.4% of the 31 effects are low order. That means more than half the effects in a full 2 to the 5 are 3-way and higher. At 6 factors, it is only 33%, and at 7 factors, just 22%. The implication is stark. As the factor count grows, the full factorial spends an ever-increasing share of its degrees of freedom on effects that sparsity tells us to ignore. Fractionation simply makes that decision explicit at the design stage rather than the analysis stage. For our coding study, we are sacrificing the ability to cleanly estimate 16 high-order effects we would have discarded anyway. Now let us be precise about the mechanism. Every run in a factorial design contributes exactly 1 degree of freedom. After spending 1 degree of freedom on the grand mean, a design with n runs has n-1 degrees of freedom to allocate across effects. A full 2 to the k uses all of them. The problem arises when you want to add a factor without adding runs. That new factor needs a degree of freedom. There are none left. The only solution is to let the new factor share a degree of freedom with an effect that already exists. That sharing is confounding. 2 effects occupy the same degree of freedom, and the data cannot tell them apart. The key insight is that confounding is not a flaw you stumble into. It is a choice you make deliberately. The question is not whether to confound, but which effects to confound with which. The notation 2 to the k minus p captures this precisely. You are studying k factors. You are running 2 to the k minus p observations. The p tells you the extent of fractionation. P equals 1 is a half fraction, p equals 2 is a quarter fraction, and so on. Each unit increase in p halves the run count and doubles the confounding. For our coding study, k equals 5 and p equals 1, giving us 2 to the 4 equals 16 runs, exactly half the full factorial. Let us do the degrees of freedom accounting for the coding study explicitly. We have 16 runs. 1 degree of freedom goes to the grand mean. That leaves 15 degrees of freedom for effects. A full 2 to the 5 would give us 31 effects to estimate. The shortfall is 31 minus 15, which is 16. We have 16 fewer degrees of freedom than effects. That shortfall is not a problem to be solved. It is the price of the half fraction, and it is paid in a specific currency. Each of our 15 degrees of freedom will carry not 1 effect, but 2 confounded effects. The ledger makes this concrete. Total runs 16. Spent on the grand mean 1. Available degrees of freedom 15. Effects in the full 2 to the 5 31. Shortfall 16. Design notation 2 to the 5 minus 1. Fraction of the full factorial 1/2. Every one of those 15 available degrees of freedom will carry a pair of confounded effects. The design notation encodes the deal precisely. Now the question becomes, which effects get paired together? That is controlled by the generator. Before we can work with generators and alias structures, we need one piece of arithmetic. When we multiply effect labels together, we use mod 2 rules. The key rule is this. Any factor letter squared becomes I, the identity, the all ones column, and I times anything leaves it unchanged. So a squared equals I. A times I equals A. And A times B times A equals A squared times B, which equals I times B, which equals B. This is not abstract algebra for its own sake. It is the tool we use to find aliases. When you want to know what effect is confounded with, say, the AB interaction, you multiply AB by the defining word of the design and reduce using these rules. The result tells you exactly which other effect shares that degree of freedom. The generator is the design decision that sets the Pfeffry factor equal to a specific interaction of the base factors. For our coding study, the generator is E equals ABCD. We set coding thickness equal to the product of the other four factor columns. Once we do that, the defining relation of the design is I equals ABCDE, because E times E equals I. So multiplying both sides of E equals ABCD by E gives I equals ABCDE. The defining relation I equals ABCDE is the master key to the entire alias structure. Every confounding relationship in the design flows from it. To find the alias of any effect, multiply that effect by ABCDE and reduce with mod 2 rules. The generator is a choice, and it is a consequential one. Different generators create different alias structures, and the engineering team should choose the generator that places the most dangerous potential confoundings in the least harmful positions. Let us now build the coding half fraction from scratch. We start with the full 2 to the 4 factorial in factors A, B, C, and D. That gives us 16 runs with all combinations of plus and minus 1 for those 4 factors. Then we create the E column by multiplying the A, B, C, and D columns together, entry by entry, using plus minus 1 arithmetic. The result is the E column for our half fraction. The defining relation is I equals ABCDE. The match column in this table confirms what we just argued. For all 16 runs, the ABCD product column and the eDesign column are identical. Every entry shows yes. This is worth pausing on. Setting E equal to ABCD is not an approximation or a rounding. It is exact column arithmetic. The E column is completely determined by the other 4 columns. There is no new information in E beyond what A, B, C, and D already contain, which is precisely why we could add E without adding runs, and precisely why E and ABCD are permanently confounded. The design matrix is the physical embodiment of that confounding. Now we can derive the complete alias structure. The rule is simple. To find the alias of any effect X, multiply X by the defining word ABCDE and reduce with mod 2 rules. Let us work through 2 examples. The alias of A is A times ABCDE. A squared is I, so this reduces to BCDE. The main effect of A is aliased with the 4-way interaction BCDE. Now the alias of AB times ABCDE. A squared is I, B squared is I, so we get CDE. The 2-way interaction AB is aliased with the 3-way interaction CDE. Notice the pattern. Main effects alias with 4-way interactions. 2-way interactions alias with 3-way interactions. This is a resolution 5 design. The lowest order alias of any main effect is a 4-way, and the lowest order alias of any 2-way is a 3-way. Under sparsity, both of those aliases are implausible, which is why this design is considered very good. Here is the complete alias table for the coding 2 to the 5 minus 1. All 15 chains are shown. Look at the structure. Every single chain pairs a main effect or a 2-way interaction with a higher order term. There are no 2-way plus 2-way aliases anywhere in this design. That is the hallmark of resolution 5. Main effects are clear of 2 ways, and 2 ways are clear of other 2 ways. The only aliases are with three-way and four-way interactions, which sparsity makes implausible. This is a genuinely favorable alias structure. The engineering team can estimate all 5 main effects and all 10 two-way interactions without any two-way versus two-way ambiguity. The price they pay is that each estimate technically includes a higher-order alias, but one they can confidently attribute to the lower-order alias, term. Let us be precise about what an effect estimate from a half fraction actually represents. When you compute an effect estimate from the data, you are not estimating a single effect. You are estimating the sum of two confounded effects, the effect of interest plus its alias. The estimate equals theta x plus theta a is of x. You cannot separate them from the data alone. The interpretation rule follows directly from sparsity if the alias is a three-way or higher interaction, and if you believe sparsity holds, then theta alias is approximately 0, and the estimate is essentially theta x. You attribute the estimate to the lower order term. If both terms in the alias chain are two-way interactions, you cannot make that attribution. Both are plausible, and you must report the ambiguity. The interpretation rule in practice, in effect, is free and clear when its alias is of order 3 or higher. Under sparsity, the alias is negligible, and a large estimate is attributed to the lower order term. For main effects aliased with 4 ways, this is almost always safe. For 2 ways aliased with 3 ways, it is usually safe but worth flagging. For 2 ways aliased with other 2 ways, which does not occur in our Resolution 5 coding design, but does occur in lower resolution designs, you must report the ambiguity honestly and, if the chain is large, recommend follow-up runs to resolve it. Now let us estimate the effects from the actual coding data. We fit a linear model to the 16 observations using the coded factor columns. The effect estimate for each factor is twice the regression coefficient on the coded scale. That factor of 2 arises because the coded factors run from -1 to +1, a range of 2, so the coefficient represents half the effect. Once we have the estimates, we attach each one to its alias chain and apply the interpretation rules. Here are the effect estimates sorted by absolute size. The largest effect by a considerable margin is the E plus ABCD chain at 13.4 units. This is a main effect plus 4-way chain. Under sparsity, we attribute this confidently to E coding thickness is the dominant driver of adhesion strength. The second largest is B plus ACDE at 7.32. Again, a main effect plus 4-way chain. We attribute this to B catalyst load is the second most important factor. Third is the AB plus C demols CDE chain at 7.00. This is a 2-way plus 3-way chain. Under sparsity, we attribute it to the AB interaction, the joint effect of cure temperature and catalyst load. That is a meaningful finding. These two factors do not act independently. The D plus ABCE chain comes in at -2.08 negative, meaning higher mixing speed reduces adhesion, but the effect is modest. The remaining chains are all below 1.3 in absolute value, which is small relative to the dominant effects. The C plus ABDE chain at 1.25 and the CE plus ABD chain at 0.914 are worth noting but not alarming. Critically, no 2-way plus 2-way chain appears anywhere in this design, and none of the small chains are large enough to worry about. The picture is clean. The half-normal plot gives us a visual confirmation of what the table showed. On a half-normal plot, you plot the absolute values of the effect estimates against the quantiles you would expect if all effects were pure noise, that is, if they came from a half-normal distribution centered at 0. Points that fall along the reference line are indistinguishable from noise. Points that pull away from the line, especially in the upper right, are the active effects. In this plot, three chains stand clearly apart from the reference line: E plus ABCD, B plus ACD, and AB plus CDE. Everything else hugs the line. This visual separation is consistent with the numerical table. Those three chains are real, the rest are noise. The half-normal plot is particularly useful because it does not require a formal significance threshold. The separation is visible by inspection. So, what did the coding study actually find? Coding thickness, factor E, is the dominant driver of adhesion strength with an effect of 13.4 units. Catalyst load, factor B, is the second most important factor at 7.32, and the interaction between cure temperature and catalyst load, the AB chain, is active at 7.00, meaning you cannot optimize A and B independently. Importantly, no unresolvable two-way collision appeared among the large chains. The resolution 5 structure protected us. Every large estimate could be attributed to a specific low-order effect without ambiguity. Now let us be honest about what the half fraction cost us. A full 32 run 2 to the 5 would have estimated every effect cleanly, with no aliasing at all. With 16 runs, every degree of freedom carries two confounded effects. In this study, the aliasing was manageable because the design was resolution 5 and the large effects all fell in favorable chains. But that is not guaranteed. The practical lessons are these. Always report alias chains to the client, not bare effect names, saying E is significant without disclosing the ABCD alias is incomplete. Choose the generator deliberately because the generator controls where the ambiguity lands, and if a large effect appears in an unresolvable chain, say so clearly and recommend the follow-up runs needed to break the alias. Let us reinforce these ideas with a second example. An injection molding team wants to study 4 factors: mold temperature, injection pressure, cooling time, and screw speed. They can afford only 8 runs. The generator they choose is D equals ABC, which gives the defining relation I equals ABCD. This is a 2 to the 4 minus 1 design, 4 factors, P equals 1/8 runs, 1/2 of the full 16 run factorial. The alias structure will be different from the coding study, and importantly, the resolution will be lower. Here is the injection molding design matrix: 8 runs, 4 factors. The D column, screw speed, is entirely determined by the A, B, C columns through the generator D equals ABC. The response is shrinkage. The construction is identical to what we did for the coding study. Start with the full 2 to the 3 factorial in ABC and derive D as the column product. The shrinkage values range from about 9 to 27, suggesting there is real variation to explain. To find the alias pairs for this design, we multiply every effect by the defining word ABCD. The alias of A is A times ABCD equals A squared BCD equals BCD. The alias of AB is AB times ABCD equals A squared B squared CD equals CD. Notice what just happened. The alias of the two-way interaction AB is the two-way interaction CD. This design is resolution 4, not resolution 5. Main effects are aliased with three-way interactions. That is fine under sparsity. But two-way interactions are aliased with other two-way interactions. That is the unresolvable situation we flagged earlier. Here are the effect estimates with their alias chains. The A plus BCD chain is the largest at 11.4, a main effect plus three-way chain attributed to A, mold temperature under sparsity. The C plus ABD chain is next at 7.24, attributed to C, cooling time. Both are clean attributants. Now look at the AB plus CD chain at 1.7. This is a two-way plus two-way chain. The estimate is not large, about 1.7, but the honest statement is this. We observe an effect of 1.7 in the AB plus CD chain, and we cannot determine whether it comes from the mold temperature by injection pressure interaction, the cooling time by screw speed interaction, or some combination of both. The data simply cannot tell us. The same applies to the AC plus BD chain at minus 0.688 and the BC plus AD chain at minus 0.434. Both are unresolvable, though both are small enough that the practical impact is limited. The B plus ACD chain at minus 0.848 and the D plus ABC chain at 0.306 are both main effect plus three-way chains and are small. Neither factor appears to be an important driver of shrinkage. The takeaway from this example is that resolution 4 designs are workable but require more careful communication. The main effects are clean, the two-way interactions are not. If any of those two-way plus two-way chains had been large, the team would face a genuine ambiguity that only additional runs could resolve. That is the cost of going to 8 runs with 4 factors, and it is a cost the team should understand before they commit to the design.